Okay, thank you. Okay, let's go ahead and get started. All right, so we've been talking about photodissociation. Last time we talked about pump probe methods for how to look at the rates and the dynamics of photodissociation. And the topic for today is going to be RRKM theory, which is the theory for describing rates of photodissociation, essentially. So we're talking about photodissociation. And RRKM, it stands for the names of the people who developed the theory, which is Rice, Ramsberger, Kassel, and Marcus. This is the same Marcus of the electron transfer theory. Okay, and so basically we've talked about rates of thermal reactions using transition state theory, but RRKM theory is the rate when you don't know the temperature, but you know the energy, which is the case in a photodissociation reaction. So basically the goal is to determine the reaction rate, the rate of reaction, as a function of the excitation energy E star. So this is defined as the rate at which a molecule with energy decomposes to products. Maybe I'll try a different pen. This one's a little bit maybe getting empty. Okay. And so if we draw a picture of this process, basically we have a reactant. We'll call the reactant A. And it has a certain 0 point energy. And then it has to undergo a reaction to make products. And I'll draw this not quite so tall so that I leave myself a little bit more space. Okay, so there's some large barrier to the reaction. It has a 0 point energy here. And so basically the threshold energy, we can call that E0. And the total amount of energy that we excited with is called E star. So you take a photon and it excites the reactant to some energy E star. I'll put that here maybe. So this energy is E star. And so the excited reactant molecule, we can call that A star, right, with energy E star. And then it has to react. And so similar to transition state theory, we're going to say that there's some sort of activated complex that's above this barrier. We can call that, it's typically called A+. Okay? And just like in transition state theory, we're going to say there's some sort of, quote-unquote equilibrium between A+ and A star. And so what about the energy of A star? Well, if this energy is E star, then we can call this total amount of energy E+. And we can decompose E+ into different types of energy. So this activated complex, it's going to have a certain amount of vibrational energy, EV, a certain amount of rotational energy, ER, And then the rest of the energy, we'll call that X. And the energy that we're calling X is going to be translational energy in the direction of the reaction coordinate. Okay? And so then this decomposes to make products. Okay? So just to be clear, this axis is energy, and this axis is the reaction coordinate. Okay? So, like we've sort of already said, this energy E plus, that's the energy that is available to this activated complex, and that is equal to the vibrational energy plus the rotational energy plus the translational energy. Okay? And so sort of in analogy to our transition state theory treatment, our approach is going to be as follows. We are going to first calculate the concentration of activated complex from the equilibrium between A star and A plus. And then we're going to multiply that by the rate at which A plus falls apart to make products. Okay? So this first part, how do we do that? Well, we're going to use statistical mechanics arguments. So this equilibrium constant, it's going to be defined as the ratio between the A plus configuration and the A star configuration, right? How many molecules are in this configuration versus this one. And from statistical mechanics, this is just equal to a partition function for the activated configuration versus the partition function for the reactant with an energy E star. Okay? So this concentration then is going to look like this. Okay? So that's basically our strategy for number one. And then number two, we have to multiply that by the rate at which the activated complex falls apart to make products. And so the rate constant for product formation is 1/2. We're going to say it's 1/2 K plus by definition, where K plus is the total rate for disappearance of A plus. To either the reactant well or the product well. Right, so we multiply by a half because half of the activated complexes have a velocity towards the reactant well and half of them have a velocity towards the product well. Right, they have a well-defined velocity because we've specified the kinetic energy x. Right, that's the translational energy along this reaction coordinate. But we don't know what direction it's in. Okay? Question?
Why 1/2?
So K plus is just the rate at which this, this activated complex is moving across the barrier. But it could be moving this way or it could be moving this way. And only the ones that are moving towards the product well react. Okay, so yeah, so we could write the rate of formation of products is 1/2 K plus times the concentration A plus, which, substituting this equation up here, that's going to be 1/2 K plus times Q plus over Q star times A star. Okay? And so assuming that this is a first order rate constant, right, which it should be if it's a unimolecular process, we can say that we can identify this part here as the rate constant. So this part here, this is our rate constant Ka of E star. Okay, so now we can consider what is this K plus equal to, right? So we have a certain barrier, and maybe it's not all that well defined, but let's say it has a certain width. We can call the width of the barrier delta. And then we have a particle that's going across this barrier. It has a mass of mu, which is the reduced mass for the reaction coordinate. Right? So if you're breaking a bond, it would be the reduced mass of the two fragments, basically. And so this is going across the barrier, and its velocity, we can write that in terms of x, because we know that the translational energy is x. So therefore, the velocity is going to be v equals square root of 2x over mu. Okay? And so the amount of time, right, is just going to be the distance over the velocity. And so the rate is just 1 over the amount of time. And so K plus, right, the rate at which the barrier can be crossed, that's going to be the velocity divided by the distance that it has to travel. So in other words, this is square root of 2x over mu over delta or a little bit simpler way of writing it, 2x over mu delta squared, quantity square root. Okay. So we have a sort of something that we can substitute here. So now we want to know what's this ratio of these partition functions. So Q plus over Q star, that's the number of states at energy E plus divided by the number of product or reactant states at energy E star. Okay, and the number of states, you can write that as the density of states, which I'll call N, right? So this is the number of states per unit energy. Times some very small energy interval, right? That's the number of states. So density of states times the, however wide your energy interval is. Okay, and you can divide that by the density of reactant states times d. Okay, and so in this expression, the dE's are going to cancel, and so this is just going to equal the density of states of the activated complex divided by the density of reactant states at the same energy. Okay, and M here is density of states defined as number of states per unit energy. So maybe I'll leave this diagram here. And so, well, maybe I'll write above here. So if you look at, states, where the states are with respect to energy, if you have only a few states, then this would have a low density of states. But if you had a situation like this, where you have lots and lots of energy, lots and lots of quantum states with very little energy in between, then this would be a high density of states. So in general, you would expect the density of reactant states to be much greater than the density of A plus states, because this has a higher energy relative to the minimum of the well. And probably you're only a short distance above the activation barrier. Okay, and so the density of states of the reactants, right, in the reactant well, this is a really high density of states, right? It looks like this. And basically, you can approximate it as a continuous function. You don't have to think about every single discrete state. You can just say there's a certain density of states everywhere. So this density of reactant states can be approximated by a continuous function. Then you can get that continuous function usually from spectroscopic constants, or at least you can estimate it from spectroscopic constants, right? The what's the frequency of each normal mode, and what's the anharmonicity of each normal mode? Then you can sort of figure out, okay, how much density of vibrational levels should there be at a certain energy? But usually the amount of energy in the activated complex is small enough that we cannot approximate it as a continuous function. And so to evaluate n plus, right, the density of activated complex states, you have to take into account the discrete energy levels. Okay. So how do we do that? Well, let's let P of E plus, and this is a vibration rotation state, so this is the energy of the vibration plus the energy of rotation. If you let that equal the probability of finding a vibration rotation level at energy E plus VR, then, you know, if each level is discrete, then this is just equal to, well, usually it's equal to 0, unless you happen to be exactly at the energy where there's a level, and then it's equal to 1. You know, or maybe it's equal to the degeneracy of the level. Okay? And so the total energy in the activated complex then, it's the vibration rotation energy plus this translational energy. And the translational energy levels are usually really, really close together, right? So we don't have to treat every single level discretely. We're going to treat those as a continuum. We're going to say there's a continuum of, or approximately a continuum of translational energy states. Okay, so for a given value E VR plus, the density of activated complex states, that's going to be the probability of having a vibration rotation state at energy EVR times the density of translational energy states along the reaction coordinate, where X is equal to E plus minus EVR. It's just the remainder of the energy that you need. Okay? And so what is then the total density of E plus states? Well, you have to basically sum over all the possible amounts of vibration rotation energy. From 0 to E plus would be the maximum amount of vibration rotation energy that you could have. Okay, so, and for every vibration rotation state, you have a translation state with energy x, but there's a certain density of those states because we're considering them to be continuous. Okay, so what is this continuous function then? Well, we can consider it to be basically a particle in a one-dimensional box of length delta. So the translational energy of a particle in a one-dimensional box of length delta so that's going to be the energy of a particle in a box state, right, which has quantum number n, and a one-dimensional particle in a box, you might recall, has energy n squared times Planck's constant squared over 8 times the mass times the length of the box squared. Okay, and so if you solve this for n, n is going to be 8 mu delta squared x over h squared. And the whole thing, you need to take the square root. Right, and so if you're at the energy corresponding to the nth one-dimensional particle in a box state, the particle in a box states are all singly degenerate, right? And so the quantum number n, that is equal to the number of states with energy less than or equal to this translational energy x. Does that make sense? And so we want to know the density of states. So we want to know what is the number of states with energy between x and x plus dE. Right, and so that's going to be, there's there's going to be some dn states in that interval, and it's going to be dn dx de, right? So the density of those states, of the translational states along the reaction coordinate, is just going to be dn dx. Right, so n is the total number of states with energy less than or equal to x, and so the rate at which n increases with energy, that's the same as the number of states per unit energy. Right, how many states do you add per unit energy? That's the density of states. Okay, so all we have to do is take the derivative of this function with respect to x, and that's the density of translational states. Make sense? Okay, so the density of translational states along the reaction coordinate so this function is basically just a constant times x to the 1/2. And so when you take the derivative, you get a constant times x to the -1/2 divided by 2. If we put the 2 inside the square root, then we get 8 divided by 4 inside the square root makes 2 times mu times delta squared over h squared. And then we need x to the -1/2, so we're going to put x in the denominator inside the square root. Okay? Okay, so now we've derived all the different parts, so now we can put everything together. So the rate constant, just to remind you, I think I erased it. It's equal to 1/2 times the rate of crossing the barrier times the ratio of the partition functions for the number of configurations of activated complex divided by number of configurations of reactant. Okay, and so this is equal to I already erased it, but if you recall, the rate of crossing the barrier, we found this just from the velocity corresponding to this translational energy, right? So it's velocity divided by distance delta gives us the rate of crossing the barrier, and that was 2x over mu times delta squared, square root. And you know what, I'm kind of running out of space, so why don't I go to the other side of the board? Instead of trying to write this all here, I'll go back over here. We probably don't need this diagram anymore. If we do, I can draw it again. Okay, so Ka, right, the rate constant at energy E star, continuing from over there, it's 1/2 times K plus. K plus is the square root of 2x over mu delta squared. And then we need the ratio of these partition functions. And so the Q plus, we have to add together the discrete vibration rotation states and then multiply that by the density of translational states with the correct energy to get, E vibration rotation plus E translation equals the total amount of energy of the reactive complex. So we have to take a summation over all the EVR states from 0 to E plus. And we're going to take the probability that there's an EVR state at that EVR energy times the density of translation states, which is, we just derived that, that's 2 mu delta squared over h squared x, quantity square root. Okay, so this is Q plus, so we still need the Q star in the denominator. Right, but yeah, so actually we argued Q plus over Q star, it should just be the density of A plus states divided by the density of the A star states. So actually this is the density of A plus states, so we just need to divide by the density of the A star states. Right, density of reactive complex states divided by density of reactant states. Okay, and so if you look at this expression, maybe it would be more accurate to write the summation out here because it's understood that you always take x, both here and here. X is equal to the E plus energy, right, total energy minus vibration rotation energy. And so there's a lot of cancellation that's going to happen, right? You have root x is going to cancel with root x, mu is going to cancel, delta squared is going to cancel. You have square root of 2 times square root of 2 is going to cancel with 1 over 2. Right, so a whole bunch of cancellation is going to happen. And after we cancel everything, we're just going to get 1 over, okay, so we're left with the square root of h squared, which is h, right, 1 over h. And then in the denominator, we have an n star, right, density of reactant states. And then we're left with just the sum over all energies of the probability of having a certain vibration rotation state at that energy. Okay, and so this summation, this has a special name in RRKM theory. This is just called W of E plus. And the interpretation of W is quite simple. It's just the number of, I'm right on time. Vibration, rotation states of the activated complex with energy less than or equal to E plus. Okay, and then the final expression for the rate actually ends up looking quite simple. It's just this sum of all the vibration rotation states at or below the energy divided by h times n star of E star. Okay, so basically, just to give you a sort of a picture to have in your mind, right? So you have a certain energy that you excite to, E star. And so there's a certain density of A star levels, right? And the partition function is equal to the ratio of the total number of levels here with the total number of energy levels here. But the energy levels here, we've divided them into vibration rotation levels, which we treat discretely, and translational energy levels. And so basically we've canceled out the contribution of the translational energy, and what we're left with is just the sum of all the discrete energy levels up to this photolysis energy. So basically you take the ratio of this density, or I'm sorry, you take the ratio, so you sum up these levels, right? The sum equals W. Right, so in this case, W would be 1, 2, 3, 4, 5, 6, 7, right? And then you divide W by the number of states here per unit energy. And then you divide by H, and that is the RRKM rate constant. Maybe if we have a few minutes left, I can quickly show you a slide or two. Oops. We don't have time for the next full topic, but I really don't like all these tables. Any questions while this is coming up? Okay, so just as an example, here are some experimental results using the pump probe method, which we talked about last time on Monday. So in this case, we're using very fast laser pulses, and we're changing the delay between the pulse that excites the system to energy E star, and then a second pulse that probes the product. And let's see, we're looking at okay, so the first laser pulse is used to photodissociate NO2, and then it dissociates into NO. And we're just above the dissociation threshold for NO2, which is at about 25,000 wave numbers, right? 25,000 reciprocal centimeters. And then a second picosecond laser pulse comes later, and it probes the NO product, right? And then you vary the delay between the two lasers, and you plot the amount of signal of NO product as a function of time, as a function of delay between the lasers. And so when you're right at the threshold for ionization, or sorry, for photodissociation, you can measure a certain energy. So shown here is the width of the first laser profile. This sort of gives you an idea what's the time resolution of the experiment. So when you're right above the dissociation threshold, you can measure a certain rate. It's, I don't know, it looks like maybe 6 or 7 picoseconds or so. But as you go higher in energy, above the dissociation threshold, the rate goes faster and faster. And it increases, at least exponentially with energy. And the reason why it goes much faster is because we're quite high in energy in the NO2 reactant well. And so as you increase the energy, the density of states of the NO2 grows very, very quickly. And it grows much faster than the density of states of A+, right, of the reactive complex, because the reactive complex is still at relatively low energy, so there's only a few vibration rotation levels available. Actually, I'm sorry, I said that backwards. Let me correct myself. I'm sorry, so we're only increasing the energy a little bit in this diagram. And so the fractional increase, yeah, I said this completely wrong, my apologies. The fractional increase in the density of states over a narrow energy region is only small. It's a large number, but it's not, it's increasing rapidly, but only by a small fraction over a narrow energy range. But the number of states summed up of the total number of accessible vibration rotational states of the activated complex increases by a relatively large fraction, right? If you go from this energy to maybe this energy, then you go from having 7 states to like 14 states or so. So you might increase this number by a factor of 2, and this number maybe increases by only a few percent. Since the E star energy is only increasing by a small fractional amount, but the E plus energy is increasing by a large fractional amount, right, relative to its magnitude. Okay, we're out of time, so actually one thing, I sent an email about doing a problem session for the homework. I didn't get any responses. I assume that's because everyone's busy thinking about cumulative exams and things like that. Does Monday work, or is that, do you have a conflict on Monday evening?
No.
Okay, let's schedule it for Monday evening. I'll send out an email.
Okay.
Because I have a feeling it might be useful to have an opportunity to discuss